Okay. Hi, everyone. First of all, I want to thank my committee member and all the guys here for attending my dissertation. My name is Yanzhou. Advisor is Dr. Ostani. My dissertation title is Real-Time Product Structural Validation for Fused Filament Fabrication. So the slides contains 6 parts. The first one is objective, the second is motivation, and third is in situ monitoring for fused filament fabrication process. And the fourth one is machine learning based structural validation. The fifth is segmentation based finite element analysis structural validation. And the last part is contributions and summary. The project objective is to reduce part-to-part variations and guarantee product structural quality during the printing. And the developed algorithm for product structural quality guaranteeing should have the abilities such as cyber physical defect detection, product structural validation, and a smart decision-making system. And the last part is quality damage warning. That means when there is a impactful defect happens, a damage warning should pop up to alert the user to make the further decision. So the ultimate purpose is to provide a printing cycle product quality guarantee management. In other words, when the product is finished and pulled off from the 3D printer, it is ready to go without any structure problem, without any structural quality problem. Here is the motivation of this project. So additive manufacturing includes various technologies. We may be familiar with the material extrusion and also the powder bed fusion. My research covers both on material extrusion and the powder bed fusion, but in this dissertation, I only focus on the material extrusion, which is the fused filament fabrication. So the printing process for the fused filament fabrication contains 3 parts. The first, design your CAD model and save it as a STL file. And in the file preparation process, the CAD model will be sliced by the slicing software, which will generate a G code. The G code contains all the printing configurations and the moving path. And then you can use a 3D printer to print out your CAD model. In my project, I will move this the product generated G code. The details will be presented later. So the fused filament fabrication has unique features like the cost effectiveness and has the ability to build a complex geometries. But based on the previous research, there is a 20% failure rate for the unskilled users. We may also make such failures in our printing process, like the corner cuppage, the bonding gaps, the layer cracks, and sometimes there is some infill defects, and also the geometry errors. Some of the defect has significant impact on the final product's structural quality, like the bonding gap or the layer crack. Therefore, it is essential to develop a structural quality validation system to guarantee the whole printing product's quality. So that's our motivation. From our review paper, in situ monitoring for fused filament fabrication, which was published on additive manufacturing, we found a lot of defect detection system has been developed and also achieved good results. Here are some examples. So in this project, two different algorithms are used for detect the defect, and the input data in this project is the vibration signal obtained from the building platform and the extruder, and the least square support vector machine is used to detect the filament jam, and the back propagation neural network is used to detect the corner warpage and the material stack, and they both achieve the good results, more than 90% accuracy. Here is the geometry error detection system. It also uses two different algorithms, support vector machine and convolutional neural network. The accuracy is around 98% and 99%. And what I need to mention here is this system can give out the real-time defect probability. And also, the convolutional neural network used in this project to detect the corner warpage, which achieved the accuracy of 99%. Abnormal extrusion is a common defect in real printing process. In this project, the deep convolutional neural network is used to detect the product surface quality, and after fully trained, the convolutional neural network can detect the over extrusion, good quality, and under extrusion. And in addition, with the feedback control, this system can adjust the printing parameters to mitigate the surface roughness problem. And we know that the abnormal height condition will impact the bonding quality. And in this project, the convolutional neural network is used to detect the nozzle height conditions, which achieved 97% accuracy. And the last one is the infill defect. And the figure shown here is the designed infill defect, and the author used two different algorithms, BS classifier and decision tree. And based on their results, decision tree has a better result for infill defect detection. So from the in situ monitoring for fused filament fabrication process, we conclude that the defect detection had been widely studied, but the defect-based product structural validation was ignored. And the final purpose for the defect detection is to guarantee the final product structural quality. And therefore, the product structural quality is an essential part which needs to integrate it into the defect detection system. And a more advanced system should integrate the real-time feedback and defect mitigating. So based on the previous summary, we proposed a machine learning-based structural validation approach. So here is the diagram for the real-time structural validation. It contains three parts. The first one is offline decision boundary training, and the offline defect detection training, and the last part is online real-time decision making. So compared with the previous method, this method can infer the defect impact and then conclude how the defect impact influence the final product quality. Based on the defect impact decision boundary, the system can make the right decision to continue or to cancel the printing. So here is the flowchart with more details. So first, we will design a lot of samples with different defects. Then we will print all samples out, and we will collect the printed samples and also get the layer image for every sample, and the images will be labeled to training the convolutional neural network. And the tensor test will be done on all the collected samples, and the tensor test result will use supported vector machine to plot out the defect impacting decision boundaries. And in the real printing process, one layer image will input into the fully trained machine learning model here, and the machine learning model will output the defect information, and then those defect information will be evaluated on the defect impacting decision boundary. Then we can judge whether the existing defect impacted the product structure quality or not. And based on the evaluation result, and the decision-making system will make the right decision. If it exists the impactful defect, then the system will cancel the printing. If the existing defect or this layer is good, then we can continue the printing. So this process will repeat until the whole product is finished or some impactful defect occurs. So here is the experimental platform. The 3D printer we used is the Creality N5, and the optical camera is fixed about on the frame about the extruder to capture the layer image. The unique feature for N5 is that when every layer is finished, the building platform will sync. So it always keeps the same distance between the camera and the printing samples. This is important for our future research, because I will explain it later. And here is the dimension. Here is the dimension for the designed dog bone samples. And this dimension is based on the American Society for Testing Material D638. So in order to achieve one of the purpose, like the cyber physical defect detection, we designed different defect, like different defect lengths and the defect on different positions. So here is the samples with defect. Like there are 3 different defect lengths and on different positions. So the red rectangular marks is the defect. So this is the seeded defect. We designed before the sample is printed out. So based on the other personal research, the stress distribution on samples varies on different layer and on different position. Therefore, we designed 30 different kind of defect styles, which is shown in the table. So it has different defect lengths and the defect located on different position. And also, all this kind of defect can happen on every layer. So the defect extraction, the defect prediction are critical for the following step. So the model we choose, the machine learning model we choose here is the convolutional neural network, which is the most famous image processing algorithm due to its ability to find the features in an image. So this convolutional neural network is modified based on LeanNet5. The input data is the layer image, and the output is there is 31 categories output, which includes the 30 different defect and also includes 1 good quality. So there is 31 output. And based on the training accuracy and the validation accuracy, it can be concluded that the proposed convolutional neural network is accurate to predict the defect for the following steps. So after we collect all the samples, the tensor test will be done. So the figure on the left shows the cross sections after the tensor test, and the product. The product here is without seeded defect, and the product here is the product with the seeded defect. And based on our experimental, so the samples without seeded defect, it always broken on this neck position. But if you seeded some defect, like there is a void defect here, if the defect is big enough or is impactful, and it will broken on this location. So after we done the tensor test, we will evaluate the product structural quality is damaged or not. So here is the tensor test result for 4 samples. So those 2 samples. So there is a minimum threshold here. So this threshold is based on the 10 average tensor force from the product with good quality. So here we choose the minimum acceptable force, like the 3% reduction from the good quality. So that means if a sample is damaged by the impactful defect, then the tensor test will be lower than the threshold. And if it's above, and then we regard this if this sample is still good. So here is the final defect impact decision boundaries. So in this figure, the red cross means the ignorable defect, and the black dot means the impactful defect. And the green part is the prediction of the ignorable defect, which means if the defect located inside of the green decision boundary, it can be ignored. But out of this green decision boundaries, all the defects will be recognized as impactful defect. So we want to evaluate how accurate the decision boundary is. So here we use the confusion matrix to evaluate the decision boundaries. Based on the evaluation result, like the F1 score, we can conclude that the decision boundary is accurate for the defect impact evaluation. What I need to mention here, you can notice the recall accuracy is much higher than the precision accuracy. The reason is that we emphasize in this project, we emphasize the recall over the precision because a 40 specimen, the misclassification of the 40 component as a functional one is more detrimental than a good one as the 41. So here we choose to emphasize the recall to make the prediction more accurate on the impactful defect. And also, let me see. I can't show the interactive decision boundary map on the website. So here so from the decision boundary, here the z-axis we use the component health indexer. So the component health indexer is a way to record the layer product quality and it contains two parts. The first part is the layer quality information here, and the right part, the right digit is the total layer with defect. So this proposed component health indexer can accumulate the effect of defect. So here is the example with more details. So the first digit, so the digit location means the layer number. So we will assign different features to this layer to indicate the each layer's layer quality. And you can see the first layer with good quality, and so there is a 0, and the 1 here means the second layer with a 1 millimeter defect, and so on. And this, the 4 here is the total 4 layer with defect. So we will use this this component health indexer to indicate the every layer's product quality. And here is the printing process. You will be more familiar with how the component health indexer works, but it's maybe too small. So the initial layer information will be all 0. That means we assume all the unprinted layers are in good quality. So we will update this layer information during the printing process. So in the printing process, the layer 1 comes to the machine learning model, and the model output, there is no defect here. So the component health index still keep as 0, and then it goes to the second layer, and still there is no defect happening here, and it goes to the layer 3. After prediction, the machine learning give out there is a defect with a 5 millimeter defect, and the location is this is the defect location, and then the component health index will update because this is the layer 3. Then there is as it's a 5 millimeter defect. Then this digit, the third digit from left will up to 5 because it's a 5 millimeter defect. And after evaluation on the defect impact decision boundary, so the final tensor test results still higher than the threshold. So it will continue because this the system recognizes this defect is ignorable. It's not impactful enough to impact the structural quality. And then the printing goes to the fourth layer, and in the fourth layer there is a 15 millimeter defect happens here, and then the system will, the component health indexer will update from here to here, and this is a 15 millimeter defect. It will update the fourth layer as 7, and because the total defect layer is 2, so it will up here to 2, and then evaluate on the decision boundary. The system found this defect is big enough. The 2 defects stacked together has impactful to the product structure. Then the system will pop up a warning window to alert the user. So that's the whole printing process. Oh now, yeah. So here is the interactive decision boundaries. So for the printing process, if the 5 millimeter defect occurs, if the defect information combined with the defect location and defect length and the component health indexer together, the defect will locate the inside of the decision boundary. So that means the 5 millimeter defect is not big enough to impact the structural quality. Then the system will make the decision to continue. But if we stick 15 millimeter defect together, and you can see the 15 is here. So if 2 layer If 2 layer, it will be here, so it's out of the impactful decision boundary. That means the accumulation defect has a big impact on the struct quality. So that's the printing process. Let's go back. Yeah.
So is it the SVM then that's determining whether something is
No. So the SVM is used for the plotting out the decision boundary. But the system will if the parameters here, and here, and all this information comes into this decision boundaries, and the system will evaluate this where is this point location. It's inside of the decision boundary or out of the decision boundary.
Isn't that what an SVM normally does?
Yeah. So the SVM will plot out this and then determine whether this position is out or inside of the. Yeah.
Okay. And that's not incremental.
Yeah. Yeah. So that's the printing process, and because what we want to achieve is the real-time structural validation. So in order to make sure the time constraint can satisfy with the current settings, we calculated the time distribution for the real-time structural validation, and personal desktop is used to calculate the time distribution here, and the time distribution starts from the layer image input into the deployed model, and then until end with the decision-making system outputs the decision. And 1,000 cycles are tested on this system configurations GPU, and the time distribution is showing here. And we can see the longest time is around 688 milliseconds, and the average for the average time for all the cycles is around 461. But and also you can notice that the image capturing and the sieving takes most of the time, and the data processing, that means the defect prediction, and the SVM decision making takes less of the time. So as 1 layer printing time needs 70 seconds. So that means our proposed structural validation system is fast enough to achieve the real-time structural validation. So here is the final warning windows when there is a impactful defect occurs on the system. It will pop up this warning window to alert. So here is the video for the real-time structural validation. So it's basically the same process as I described before. So here is the summary for the machine learning-based structural quality validation. So we achieved the defect detection with machine learning algorithm, and also we achieved the structural validation based on the decision boundary from support vector machine, and a novel component health index that links the feature with the defect across layers. And finally, we proposed a smart decision-making algorithm based on the defect impact. Even the machine learning-based structural quality validation achieved good results, but it still has some limitations. For example, the supervised learning can only predict the known cases, but it can do for the unknown cases. And also the defect impact decision boundaries is accurate, but it still has some errors. And the last one is the component health index is complex, and it is hard to record multiple defects on one layer. So in order to solve the limitations I mentioned above, we proposed a new, more advanced segmentation-based finite element analysis structural validation. So what we want to achieve is the real-time structural validation. We want to build the real-time finite element analysis by during the manufacturing process. We want to get the instantaneous evaluation and get the instant decision before the next layer is started. So here is the diagram of the real-time FEA structural validation. It also contains three parts: the offline defect segmentation model training, and online defect segmentation. And the last one is online real-time FEA structural validation. So the novelty of this method is it can automatically run the structural validation system compared with the previous research, and it will give out if a single layer or accumulated defect is impactful or not. So let's talk about the image segmentation first. So the image segmentation is an approach to break the digital image into subgroups, and image segmentation will assign different labels to pixels. There are two different segmentation approach. The first in the image segmentation. The first one is semantic segmentation, and the second is instance segmentation. For the semantic instantiation, the multiple target will be identified as the one entity. But for the instance segmentation, it will treat the same category as different categories. So you can see here there are three shapes. The segmentation, the semantic segmentation treat all the three shapes as one category, but in the instance segmentation, it will treat each shape as one category. In our research, we will use the semantic segmentation because we want to treat all the defects as one entity. And the image segmentation model we use here is the UNet, which is also the most famous image segmentation result. The model input is the image, the layer image, and the output segmentation result will be saved as the polygon lines, and which will be used for the further defect updating in the Abacus pattern script. So the Abacus offers the Python API that offers the opportunity to use the Python interface and with the interactive with the Abacus CE or Abacus viewer. So The Abacus CE can automatically generate a pattern file. This pattern file can record every operation during the session. So this is the file we will use to update our defect information. And also we know the pattern script includes those parts like the parts, the materials, and sections, assembly step, load boundary condition, and meshes. And we can also define our own function in the pattern script to achieve some specific purpose. So first of all, we will assume all the product layer quality is in good quality, and then we will do the simulation on the Abacus Abacus. This will generate the Abacus pattern script. You can see it contains everything like the sketch to draw the models and the parts and the material definition, and also this is the boundary condition and the mesh generates, and also submitted the job to analyze. So that's the Abacus pattern script we need to generate first, and this is the base for the further updating. So what we will do, we will update these three parts: the parts, material, and the meshes. So here is the figure on the right is the image segmentation results. You can see it has the category ID and the segmentation. This is the segmentation result. It will show an array. In our project, we will use this defect list to update the pattern script here. So you can see different we will use this polygon point to update the model sketch, and then some of the information are used to update the material properties. So in the output, we will traverse all the output frames to find out the maximum stress before the fracture happens. So here is the principle of the real-time FE structural validation. So there is three different defect types in this project. This is the seeded void, which is a artificial defect we seeded before, and the long short void is the defect in the real printing process. So when each layer image comes into the unit, it will give out the defect information, and we will update this defect information in Abacus pattern script, as I mentioned before. So the long and short void were used to update the void related Yanzhou modulus, and the seeded void defect will use the extrusion card to form the defect inside of the sample. So the reason why we apply two different approach is the seeded void use the extrusion cut to emphasize the sensitivity of defect. The Yanzhou modulus is a generic layer material productivity. And also we use the dynamic property for future layer, which means for the unprinted layers, we will calculate the average printed Yanzhou modulus, and then use it for the future layers Yanzhou modulus, and then we will do the online components structural validation. And also this printing process will repeat until the impactful result across all the whole impact the whole product is finished. So here is the experimental platform. It's basically almost the same with the last one, but here we choose the more powerful computer to accelerate the simulation process. And the design sample is based on the American Society for Testing Material D5677, and you can notice there is a hole here. So this specimen and the final application may require some fastener holes, or this fastener holes can allows for the stress concentration and also reduce the net section. And in the figure on the right, you can see there are some shaded void here, and also there is some short void inside of the layer, and the long void is on the edge of the printed samples. So here is the tensor test result for the samples, which is good layer, good sample, and sample with ignorable defect, and sample with impactful defect. You can notice that if the impactful defect means some defect occurs around the fastener holes, so it will dramatically reduce the tensor force. And here is the prediction, the image segmentation result. The figure here is for the good layers, and this is the layer with some defect. You can see there is some shaded defect here, and some short void and long void along the edge. And the evaluation matrix we choose here is the intersection over uni. So what the intersection over uni means? The zero indicates there is no overlap between the product segmentation and the ground truth, and the one means it's perfectly overlapped between them. So based on that, we can conclude that the proposed image segmentation result achieved a good result for defect extraction. And as I mentioned, we want to use the void-related Yanzhou modulus. So based on the David's research, so we can calculate the void-related Yanzhou modulus based on this equation. So in order to achieve the accurate results, all the material properties are derived from the real tensor test, and the parameters, the material property parameters are shown in this table, and we use the explicit scheme, and the boundary condition is one end is fixed, and one end applies fixed loading displacement, and the mesh size is 1 millimeter. Element shape is 4-node linear C3D4. And this is the final. As I mentioned before, there are two different ways to form the defect, and the shaded void defect is used the extrusion heart, and this is the final result after updated on the app, because it will, you can, it's maybe not clear. You can see there are some black dot. That's the polygon point it used to form the extrusion heart. And here is the real-time FEA structural validation process. And the first layer comes in, and there is no defect because the first layer we printed in the horizontal direction, so there is no defect, and the bonding gaps across in that layer, so it's good quality. And then it goes to the second layer, and on the second layer there is a defect here, and also can do some long short void, and all this information were used to update the pattern advocacy pattern script. But you can notice that this defect is in the insensitive position, so it will not impact the the structural quality too much, and then it will continue after we get the maximum stress from the FE result, and it's larger than the maximum stress threshold, so it will continue and go to the layer 3, and layer 3 only has a long short void and without the seeded defect, so it will still continue. And but on the layer 4, there is a defect. You can notice here, and there is a defect occurs around the fastener hole. So that means the final maximum stress will be reduced a lot. Then after analysis, the final FE result and the maximum stress is lower than the threshold. So that means an impactful defect occurs. So it will pop up the warning window here. So here is the final simulation result. The figure on the figure here is the product with good quality, and the figure here, the simulation result is from the sample with some insensitive defect inside, and you can notice the maximum stress differences, and this is the one with a defect around the fastener holes. So it will reduce the maximum. It will reduce the product quality and have a lower maximum stress. So here we choose a 4% reduction in the final maximum stress compared with the one with good quality. Also, you can notice is if there is no impactful defect on the sample, the fracture point is different, and there is one fastener hole defect here, so it will change the broken position. So it's the same. In order to achieve the real-time FE analysis, we also analyze the time constraint. Here we use a more powerful computer with 16 cores, and we do the same thing to calculate the time. And here is the final result. You can notice that the image segmentation takes a very short time, but the script sketch update takes a longer time, and most of the time are taken by the structural FE analysis. And we try to, in order to analyze the time consumption, we did different. So we did analysis on defect number and the total defect area. So what that means is, so here is one defect, and here is the second one. So we will calculate how many defect on one layer and the total defect area. So that's the two variables, and as you can see here, the computational time varies, but it's not just related with the total defect area. It also relates with the number of defects. And in order to figure out the impact of the user tokens in the validation process, we use the different tokens to find out the time consumption here. You can notice from the 4 token increased to 12 tokens, and it will save almost 20 seconds. But after that, if you increase the token from 12 to 16, the acceleration is not obvious. Because we want to achieve the real time, so we want to find out based on the current system configuration, which is the decision boundary for the unachievable or achievable real-time structure validation. From here, you can see the defector located around the yellow part is not achievable because the current sample, if one layer is printed out, it needs 140 seconds. So that means after if the defector over this line, it is over one layer's printing time. It is not achievable for the current configuration. So as I mentioned, we can define our own function in the Python script. So we defined the maximum stress extraction function, which will reverse, which will goes through all the frames to get the maximum stress, and after get the maximum stress, if it's lower than the threshold, then the FE will pop up a warning window to indicate the current product structural quality is damaged. So here is a summary of the real-time FE structural validation. So we achieve the defect segmentation and defect information extraction, and we use this information to update the defect in the Python script. And also we propose the dynamic specimen layer property, which is the void-related Yanzhou modulus. And also we achieve the real-time FE structural validation, and we achieve the decision making based on the maximum stress. So here is the last part, is the contribution and the summary. So the key contribution in this field of real-time structural validation is we did the defect detection with machine learning and also with computer vision, and we proposed a component health index that links the features of the defect across layers, and the dynamic specimen layer property. And the last one is we did the structural validation based on the defect impact decision boundaries, and also based on the FEA result, and a smart decision making algorithm based on the defect impact is made. So here is a summary of the research presented here. So we reviewed the current in-situ monitoring research for physics fabrication, and present machine learning-based real-time structural validation, and also defect segmentation-based real-time finite element analysis. Here is the publications during my 4-year study. So lastly, I want to thank my sponsors. Without their support, I can't achieve my doctoral degree. So also thanks for everyone attending my dissertation. Thank you.